Hello friends, in this session we will be talking about zeros of a polynomial. So friends, let's take a polynomial px such that px is equal to ax raised to power 4 plus bx cube plus cx square plus dx plus e. Now 0 of this polynomial is that value of x for which the value of this polynomial px becomes 0. So if a value of x results in the polynomial becoming 0, that value of x is called the 0 of that polynomial. Now if x equal to a, let's take x is equal to a, and that results in px equal to 0. That makes this polynomial equal to 0. Then we can say pa, where x is replaced by a, is equal to 0. Then a is the 0 of the polynomial and x minus a is the factor of the given polynomial, as we already know by a factor theorem. So if pa is 0, then we can say x minus a will be the factor of this polynomial and a is the 0 of this polynomial. Now supposing we have px equal to x square minus 3x plus 2. Now in this we put the value of x as 1. So we get 1 square minus 3 into 1 plus 2, which gives us 1 minus 3 plus 2 equal to 0. So x equal to 1 makes this polynomial 0. So that means x equal to 1 is the 0 of this polynomial. And by factor theorem, x minus 1 is also a factor of px. Now we already know about linear equations, quadratic equations and cubic polynomials. Actually we are talking about the polynomials, not equations. So we know linear polynomials are the polynomials where the degree of the polynomial is 1, where x raised to power, the maximum power of x is 1. That kind of polynomial is called the linear polynomial. Quadratic polynomial is where the degree of the polynomial is 2. Cubic polynomial is where the degree is 3. Now we are just going to talk about the number of real unique zeros of a polynomial. Now this is less than or equal to the degree of the polynomial. That is why we were just talking about linear, quadratic and cubic for now. So if we are saying we have a linear polynomial of the type 2x plus 3. Now this polynomial will have a maximum of 1 real unique zero, because we are saying the number of real unique zeros of a polynomial is less than or equal to the degree of the polynomial. Now the degree of this polynomial is 1. So that means the number of real unique zeros will be less than or equal to 1. In this case we clearly know minus 3 by 2 is the 0 of this polynomial, and that's the only 0 of this polynomial. So any polynomial of the type ax plus b will have a maximum of 1 real unique 0. If we have a quadratic polynomial of the type 2x square plus 3x plus 1. Now this can have a maximum of 2 real unique zeros. Similarly, a cubic polynomial will have a maximum of 3 real unique zeros. A linear polynomial, as we just discussed, can have a maximum of 1 zero. A quadratic polynomial can have a maximum of 2 zeros, and a cubic polynomial can have a maximum of 3 zeros, and so on. However, all the zeros of the given polynomial may not be unique. Now this is important because in the first statement we are saying the number of real unique zeros, and that will be less than or equal to the degree of the polynomial. Now here we are saying that not all the zeros of the polynomial may be unique in all the cases. So we take an example here. We have this polynomial x square minus 4x plus 4. Now if we see x, this can be written as x minus 2 whole square. So it has two roots, or you can say it has two zeros, but both of them are 2. So that means it does not have two unique zeros. It has only 2 as the zero of this polynomial. And why do we find zeros of the polynomial? Because that helps in solving the equation px equal to 0. So if we have a polynomial equal to 0, it helps in solving this equation, and it also helps in factorizing the polynomial. As we said that if a is a zero of the polynomial, then x minus a will be the factor of that polynomial. So it helps in factorizing the polynomial. And another important thing is some polynomial may not have any real zero. So now if the value of x does not come out to be real, then the polynomial will not have any real zero. Friends, now we are going to see how do we graphically represent the zeros of the polynomial. Now let's say we have this xy axis, we have this graph, and this is the x-axis we know, and this is the y-axis that we know, and we plot px on the y-axis. So we plot the polynomial on the y-axis and x on the x-axis, the variable itself on the x-axis. Now if we plot the graph, we'll see that, say for example, we have a linear polynomial, we'll have a graph which would be something of this type, which would be basically a straight line, and the straight line could be anywhere. Now this kind of graph, if we see, cuts the x-axis at a point. And at this point we can clearly see that we have this value of x where the px is 0. So we are saying that this point becomes the 0 of this polynomial, which is represented by this line. So we can say that any 0 of any polynomial will always result in the graph cutting the x-axis. So this is what the linear polynomial graph would look like. But if we talk about, say, a quadratic polynomial, what would it look like? It could look like this. So it would be a parabola kind of a structure in one way or the other. Now similar to this line which could have different slope, different directions, similarly this parabolic structure could be, depending upon the kind of polynomial, it could be anywhere. It could be cutting the x-axis at 2 points, it could be cutting the x-axis at only 1 point, it could be opening upwards, it could be opening downwards, and so on. So now if we see, say for example, let's take a different color here. Say we have this as the curve. Now we know it cuts the x-axis at 2 points. One is this, the other is this. So these 2 points are the zeros of that quadratic polynomial. But if we take another parabola, say for example we take something like this. Now this is cutting the x-axis at only 1 point. So although this is a quadratic polynomial, it is showing that there is only one real zero of the polynomial. Similarly, if we take a cubic polynomial, the curve could be something of this type. It could be something of this type. Now if we see this curve, it is cutting the x-axis at 1, 2 and 3 points. But if we see this curve, this is again a cubic polynomial, but it is cutting the x-axis at only 2 points. So this means that the zeros of this cubic polynomial may be only 2 unique zeros. So this is how we represent the zeros of the point of the polynomial graphically on a xy graph. The zeros of the polynomial will be all those points where the graph crosses the x-axis. And now we can say that by looking at the graph, we can find out two things. First is the zeros of the polynomial, and second is the nature of the polynomial. So we can say whether it's a linear polynomial, a quadratic polynomial, or any other, what is the nature of the polynomial, and secondly, we'll be able to tell the zeros of the polynomial. And we can also actually find out the equation of the polynomial, and when we go further, we'll see how do we do that. This gets covered in the higher classes. So friends, now we'll see some more examples of geometrical representation of zeros. Now let's take a graph. So if we have a graph of this type, now we know by looking at the graph, we know that the graph is showing a quadratic polynomial, right? We know because the parabolic graphs are for quadratic polynomials. So this is representing a quadratic polynomial. But if we see that this graph is not cutting the x-axis at any point, so this means that this does not have a real zero. Similarly, if we have something like this, we again know that this is not cutting the x-axis, so that means there is no real value of x for which the polynomial will become 0. So this is where we will see that there is no real 0. Similarly, we could have, say, a graph of a cubic polynomial. So now this may also not be cutting the x-axis at any point. So if we see that this is not cutting the x-axis at any point, then we can say, then again there is no real value of x for which the polynomial will become 0. And now we'll see, let's take another graph where we have this. Now here, or we can have something like this, and say for example x is equal to 5 here and x is equal to 0 here. Maybe we can take something like 0.2, it is not 0, right? So now we can say that this is a quadratic polynomial, but the only root is x equal to 5. So this could be a graph of x square minus 10x plus 25, because at x equal to 5, this is becoming 0. At no other value, it is becoming 0. So this has a real 0, but it does not have unique zeros. So its 0 lies at x equal to 5. So now here again we see, by looking at all of these, we can see that how just looking at the graph gives us an idea of what its zeros would be and what will be the nature of the polynomial. So now let's take the example question. We need to find the zeros of this polynomial fx equal to 4x square minus 4x plus 1. Now there are definitely a simple approach of finding the zeros where we keep putting in different values of x and finding out whether fx becomes 0. But that is a hit and trial method which is time consuming, which may not be the appropriate approach. So we could take an approach of factorizing the polynomial if it's possible. So let's say we factorize it by making it 4x square minus 2x minus 2x plus 1. So we take out 2x common from here and we get a 2x minus 1 here, and we take out minus 1 here and we get a 2x minus 1 here. So this becomes 2x minus 1 whole square, and we can just use the identity to double check it. It becomes 4x square plus 1 minus 4x. So now here we know that x is equal to half is a zero of this polynomial, and this is actually the only zero of this polynomial. Although this is a quadratic polynomial, it could have a maximum of two real zeros, two real unique zeros. So here it has two zeros, but both of them are same. So it has only one unique zero, which is x equal to half. Friends, I hope you enjoyed the session. If you find it useful, please like it and share it with your friends. You can visit us at our Cool Smart Learning website and post your queries there. And please subscribe to the Cool Smart Learning channel for getting updates on the new sessions. Thank you.